Hello, I'm Andrew SELLEK from the University of Cambridge, and I'm pleased to talk about my work on the importance of considering dust evolution in understanding observed disk demographic trends, specifically the M.M relation. I recently published this work along with Richard Booth and Cathy Clark as a dusty origin for the correlation between protoplanetary disk accretion rates and dust masses, and I've linked to it on the bottom of all the poster slides, so if you're interested you can find out more about the assumptions about the dust that we investigated. So as I've preempted, recent observational data of the disk accretion rate as measured from the UV continuum excess in the surveys by Alcalá et al. And Manar et al. Has been seen to correlate with the disk millimeter flux, which we assume traces the dust mass, measured in the surveys by Ansdell et al. And Bauernfeld et al. Now we'd expect this correlation, which is roughly linear, in terms of the total mass in viscous evolution models. I've illustrated these here for a grid of disks with different parameters in the plane of their accretion rates and their gas masses. And you can see on each track I've highlighted a section in solid which represents on the left-hand panel 1 to 3 megayears and on the right-hand panel 5 to 10 megayears as appropriate to the ages of Lupus and Upper Scorpius respectively. Now the existence of this trend when considering the dust masses has been used to argue that actually we can infer the total mass by scaling up by a factor of typically a gas to dust ratio of 100. But I think in Lupus, at least for these parameters I've looked at here, you can see that it's not wholly recovering this area of the data. You can sort of reproduce this area if you play with the parameters of your viscous model. But if you generally consider it's these disks at high accretion rate or low mass that are causing the trouble, we can also talk about this in terms of the ratio of the mass to the accretion rate or the accretion timescale, which then in this case is low for these challenging disks. And certainly in Upper Scorpius we have an even stronger problem because the accretion rates continue to decline, but in the data the accretion rates are pretty much spanning the same range at a given mass as in Lupus. And so we're finding that the data are just being totally missed by the models. So what we did was revisit this idea by simply looking directly at the dust masses themselves, because we would expect these to differ from the total mass because the dust is subject to different evolutionary processes. Specifically, it feels aerodynamic drag, which causes it to drift inwards and hence deplete faster than the gas component. So we would expect the gas to dust ratio to change both in time and with location in the disk. And you can see that when we modelled this, we found that the apparent mass that an observer would measure did indeed decline much faster, which pulled the tracks to the left towards the bulk of the data in both the younger and older regions. Now, key to actually getting this to work well is having to consider the fact that the opacity and emitting temperature of the dust are changing as the grain size and spatial locations change in response to the surface density profile of the disk. And these things combined give you this phase where the accretion rate and the mass are declining at pretty much the same rate. And so we get the tracks becoming nearly parallel to these dashed lines that represent constant accretion timescales. Moreover, for different models of different parameters, you can see that these tracks can become nearly collinear, and this also allows us then to argue that at different ages we should see roughly the same maximum accretion rate at a given mass. It's just that you've got some higher mass disks that have now evolved at roughly constant accretion timescale to the same point. Nevertheless, in both of these regions there are now some disks at low accretion rates that are still proving hard to resolve in this model. And so there could be a number of solutions to this, but we decided to focus on internal photoevaporation, because once the accretion rates become low enough, the internal photoevaporation becomes the more efficient way of removing material, and so it starves the accretion, causing the rates to decline and the tracks to turn downwards. Now, we inspected a variety of models with both EUV and X-ray driven winds and found that we couldn't discriminate between the two. But in order to get these low mass disks at low accretion rates, we had to have the dust decline sufficiently, which meant that we had to have a fairly low mass loss rate in the wind of below about 10 to the minus 9 solar masses per year. And so we think this sort of argument gives us a natural reason why we would expect not to find too many disks below the range of 10 to the minus 10, 10 to the minus 11, and this sets the minimum at a given mass across regions of different ages. Thank you.